Okay, we're back. And we're going to be talking now about calculus involving parametric equations. Now, hopefully you've had a chance to play around with some parametric equations, get a feel for them, and that kind of thing, because I'm going to be depending at this point on, that you have at least a little bit of an intuition for what is going on with these things. First thing that we want to talk about are derivatives. Well, the natural and immediate thing that we can do with derivatives is that if I have a couple of functions, x of t and y of t, we can of course define the derivative of x with respect to t, and we can define the derivative of y with respect to t. That's no problem. We know how to do that. You know how to do that from Calculus 1 stuff. But what if we now want to figure out, well, what is the derivative of y with respect to x? Or what if we want to find dx with respect to dy? One thing you could try to do is you could try to come up with some kind of a formula that relates your different variables, and then you could try to use implicit differentiation. Or if you're lucky, maybe you can actually write one variable in terms of the other variable as a function and then do it that way. But in most cases, you won't necessarily be able to do that. And even if you could, that would be a lot of work. So let's see if we can do it without having to rewrite things so that y is written in terms of x or x in terms of y or whatever we want to do there. What if we just have x of t and y of t and we don't want to write anything else? Well, here's what we can do. I want to consider this. dy by dx, this is really the limit as delta x goes to 0 of delta y divided by delta x. But this is really the limit as delta x goes to 0. And I'm going to leave aside a minor technical issue here, okay? The minor technical issue is I would like to multiply on the top and the bottom by delta t. Now, you can't do that if delta t is equal to 0. But delta t is just a parameter, so I'm going to assume that the change in t here is never 0. And that's kind of a reasonable assumption to make about our parameter. Now, of course, you can worry about things like, what happens if delta t does happen to be 0 at some place? Well, it turns out that actually you don't have to worry about that, because if delta t is equal to 0, then that means x and y haven't changed at all. Like, they can't change if t hasn't changed, since they both depend upon t. So that technical issue aside, and it's not too difficult to justify here, we can multiply the top and the bottom by delta t. But what happens in the limit as delta x goes to 0? Well, delta t is also going to be going to 0, really. And so what we can do is we can replace this with a delta t goes to 0. Because delta t going to 0 would make delta x go to 0 as well. And that's what we really want. But now, this is actually just dy by dt times dt over dx. However, dt over dx is actually going to be 1 over dx over dt. So what we can say is that dy over dx is just going to be dy over dt over dx over dt. So the derivative of y with respect to t, and then the derivative of x with respect to t. And this gives us a way that we can find the slope of a tangent line really easily without having to actually know y as a function of x or anything like that. All we need to know is x and y as functions of t. And here's an example of this kind of thing. Let's suppose that we have x of t is going to be equal to 2t cubed, and y of t is going to be equal to the sine of t, and we want to find the tangent line when t is equal to, let's say that we want it to be equal to pi over 2. I don't know. I'm just coming up with some kind of a point. Well, here's what I'm going to do. Y prime of t is going to be cosine of t. And x prime of t is going to be equal to 6t squared. So that means that dy over dx is going to be equal to the cosine of t divided by 6t squared. And so now what we can do is we can say, well, when t is equal to pi over 2, then dy over dx is going to be equal to the cosine of pi over 2 divided by 6 times pi over 2 squared. This is actually just 0, right? Because the cosine of pi over 2 is 0. And then the point that this line is going to go through, well, all we need to do now is to, since it's a line with a slope of 0, we just need to find its y value. The sine of pi over 2 is equal to 1. So the tangent line is actually just y equals 1. There we go. There is our answer. Fairly straightforward to deal with here. So let me give you another example of this to think about, and I want you to try this one on your own before you watch how I do it. So let me ask you to do this one. Let's see if you can find the tangent to the line given by the parametric system of equations. X of t is equal to cosine of t, and then y of t is equal to e to the t plus sine t when t is equal to, let's say, what do we want to do here? So now I'm going to get myself in trouble, aren't I? Because I didn't think this far ahead when I came up with this problem. Actually, to make things nicer, I'm going to make this into e to the t plus cosine t, and we're going to make x of t equal to sine of t. So let's do when t is equal to 0, because that one I know is going to work out fairly nicely. So again, take a minute to try to figure this out. So let's see if we can work this together then. X prime of t is going to be equal to the cosine of t. Y prime of t is going to equal e to the t minus the sine of t. Now, when t is equal to 0, what we're going to get is that dy over dx is going to be e to the 0 minus sine of 0 divided by the cosine of 0. Well, this is just 1 minus 0 over 1, which is equal to 1. So this tangent line is going to have a slope of 1. And then what point is it going to go through? Well, x of 0 is equal to 0, and y of 0 is equal to e to the 0 plus cosine of 0, which is equal to 2. So if I use the point slope form, this gives me y minus 2 equals 1 times x minus 0. And of course, if we wanted to, we can write this as y equals x plus 2 or whatever. But there we go. We have gotten our tangent line written here. Now I want to show you something really cool about this. Somewhat obvious, but rather cool. What happens if we start thinking about the unit circle given by x of t equals cosine t, y of t equals sine t. Well, x prime of t is equal to negative sine t, and y prime of t is equal to cosine t. So what ends up happening is that at any given point, dy by dx is going to be equal to the cosine of t divided by, oh, hey.
Keep going.
No, I'm pausing this. Okay, sorry, one of our new adjuncts was dropping by to see me, so sorry about that delay. So anyway, the derivative of y with respect to x, right? We've got y prime over x prime. Well, that's cosine t over negative sine t, which is actually, if you go back and you look at these original formulas that we've got, well, this is actually negative x over y. This is not at all surprising, okay? We have seen this before, right? We've done this when we did implicit, well, okay, we, not you and I, but you have hopefully done this before, because when you took calculus 1, when you do implicit differentiation, one of the things that you find is that the dy by dx for the unit circle is just negative x over y. And this is, again, not even remotely surprising, right? Because, okay, we're going to get into here a little bit of a thing here that maybe isn't directly related necessarily just to parametric equations, but it's interesting enough that I think it's worth taking the time. So we got this unit circle, right? And my ability to draw circles is virtually nil, so bear with me. Now, here's the thing. If I am out here at some point, what is the slope of this line? Well, the slope of this line is going to be sine t over cosine t, right? It's the change in y per change in x, which is sine t over cosine t. In other words, the slope is the tangent. Well, what is the tangent line? The tangent line should be perpendicular to the radial line. That means the slope is going to be the negative reciprocal of it. And therefore, yeah, that is exactly what we find in this case, is that, see, before we had the notion of tangent lines defined using calculus, the very first, to my knowledge, definition of a tangent line was tangent lines to a circle, where you can say, it is the line which is perpendicular to the radius and touches the circle. Well, what it turns out, what we're really saying here is that the tangent line defined via calculus agrees with what we say the tangent line ought to be for the circle. This is a good thing. It is always nice when our expectation ends up being matched by what we end up defining, right? We expect that this should be the tangent line here, and therefore it should have a tangent slope of negative cotangent, the negative reciprocal of this thing. Well, that is exactly what we have found. All right, so kind of a minor aside from just directly working with the parametric equations, but I figure worth taking a minute to say why that is true. In fact, you can go beyond this and say that in some sense, you think about how this thing is moving. Well, at any given point here, we should be moving at, if I have x of t equals cosine t and x prime of t equals negative sine t, then the rate at which I'm moving is 1. Like if I've measured my velocity at any given time, it is equal to 1. And then from what this tangent line should be, you can pretty easily work out a guess that the derivative of cosine must be negative sine, and the derivative of sine must be cosine. Why? Because if I walk around this circle at a unit pace, my velocity is 1, the direction I'm facing should be this tangent line. Well, the direction I'm facing is therefore negative cotangent of t, or it is proportional to the negative cotangent of t, at least. So it's negative some constant times cotangent t. And to work out what that ought to be, I can work out, well, okay, that has to come out to be 1 because I'm moving at a rate of 1. And then I can say, but actually what that means is that the rate at which my x variable is changing must be negative sine t, and the rate at which my y variable is changing must be cosine t. So if I didn't know these derivatives, I could say from this reasoning, this is what those derivatives are going to have to work out to be if these functions are differentiable at all. The only tricky part here is proving that these really are differentiable functions. So you remember back in Calculus 1, you have to do a fairly sophisticated geometric argument to show that the derivative of sine is cosine. Well, actually, the only really tricky part is showing that it's differentiable at all. If you can get that, then it's easy enough to show that the derivative has to be cosine. Like, intuitively, that's exactly what you would expect. I'm not sure if my explanation there was very clear or not. Don't worry too much about it. It's just an interesting factoid that I wanted to mention. But yeah, so let's move on to talking about some other stuff that we can do with parametric equations. Now, the two things I want to focus on here are going to be the following. So one thing that we can say is, what about the arc length? From t equals a to t equals b. It turns out that finding the arc length is actually really quite straightforward, okay? And the reason is because in order to find the arc length, let's think back to what we did when we calculated arc length the first time, right? What we did the first time is we said, okay, we have some kind of a curve, and we're going to split it up into a bunch of straight lines. And then on each of these lines, we're going to have some sort of change in y and some sort of change in x. Okay, well, that's perfectly fine. And then we can say that the total length is going to be the sum from I equals 1 up to n of the square root of delta x squared plus delta y squared. And then what we observed is that, well, you could factor out a delta x squared here, and you get 1 plus delta y squared over delta x squared times delta x. This gave us our formula. I'd like to go a slightly different route this time. Instead, what I would like to do is I'd like to write this as the sum from 1 up to n of the square root of delta x over delta t squared plus delta y over delta t squared, all multiplied by delta t. So this delta t is outside of the square root. All I've done here is I've multiplied on the outside by delta t, and I have, to compensate for that, I got to put delta t squareds in the denominator inside of here. But watch what happens in the limit as n goes to infinity. So as we take these Riemann sums up to infinity, this is going to become the integral from a up to b of the square root of x prime of t squared plus y prime of t squared dt. And that's it. Really, I mean, this is almost anticlimactic. It's so similar to what we've done before. But to my mind, this is actually prettier than what we've done before. This is much more aesthetically pleasing because it's symmetric. We're treating x and y on an equal footing here. They both just depend upon this third variable t, and so everything, there's no difference between x and y's now. Normally, when we think about x as an independent variable and y as a dependent variable, then that's when we get this sort of, oh, there's a difference between the x's and the y's, and we have to worry about which one does which, and then, no, everything is fine here. Everything is just written out in terms of x's, y's, and this t. We can recover what we had before because in the special case where x is actually equal to t, so if I have y as a function of t, one thing that you can always do is if we have y equals f of x, you can always rewrite this as y equals f of t, x equals t. So you can rewrite this curve as a parametric system like this. And when you do that, then x prime is just 1. So you recover the previous formula from this formula really easily. Personally, And this is a personal preference that is partly based upon the fact that I've done this for many years and the way that I personally think about problems. I actually prefer to think about problems in many cases as parametric. I like to think about curves given parametrically rather than as y being a function of x or something like that. It's actually quite nice to think of them both being given by a third parameter. And then if we need to, we can say, well, if y is really just a function of x, that's a parametric system where y is f of t and x happens to be equal to t. Okay, but anyway, this is what it comes out to be. And this quantity in here, this is often written as ds. And ds stands for something whose name is for some reason really escaping me, and I should know what this is off the top of my head. Well, it doesn't really matter what it's called, but for some reason, the name of this ds is escaping me. Anyway, we write this as ds. You can think of it as the differential of the arc length, really. I mean, that's literally what it is. If s is your arc length, this is the differential of the arc length. And we can play a very similar trick to get a formula for surface areas for surfaces of revolution. Why? Because think down to what happens with the formula for the surface areas of revolution. Well, the formula that we got involved this thing involving the frustum, which really just involved the arc length, right? So why did I erase the picture that I need? I do this all the time. I need a certain picture. I make a picture. I use it for one thing. I erase it. And then I realize that I actually need it for a second thing. So if I take some curve, right, and I rotate it around to form a three-dimensional object, I'm trying to make this picture quickly, but, you know, so we get this sort of vase shape, however you want to pronounce it. What is the surface area? Well, the way that we found the surface area was we approximated this curve, again, with straight lines, and then we observed that the surface area comes out to be 2 pi times the radius here, where the radius here is the average radius. It's 2 pi times the radius times the length of this little segment. So what does that come out to be? Well, that comes out to be the integral from a up to b of 2 pi r ds, where ds is just this same differential of the arc length. So, in fact, what we can do here is we can just use this formula anytime that we want to. You know, we can, in other words, all I got to do in order to do this is replace r with the appropriate quantity. In this case, I would say, well, r is y, which is a function of t. And then I replace ds with this ds over here. And there we go. We've got our formula for surface area. Once again, to me, this is a much nicer formula than the stuff we've written down before. Because before, we had like, okay, here's the case where y is a function of x and we're doing this rotation. Here's the case where we've got it written differently for another rotation. This summarizes all of those formulas into one piece. Because notice, like, let's say that instead of rotating around the x-axis, what if I'm rotating around something else? What if I'm rotating around, like, y equals -1? So I have some curve here, and I rotate it around y equals -1. Well, in that case, I would just say r is equal to x of t plus 1. Right? It's whatever my x of t is on here. That gives me this distance plus an additional 1. And so whatever I'm doing, I can just remember this formula for the surface area and replace the radius with whatever's appropriate, replace the differential of arc length with whatever is appropriate, and use that formula. Okay, so it allows me to bring together all of these different special cases into one universal formula, one universal equation that deals with all of them. Now, let's just take a quick look at something which technically this is in your textbook, and I usually don't do the examples in your textbook. But I want to show you really quickly how to derive a very famous formula by using this. So let's show here that, well, let's suppose that we want to find the surface area of a sphere of radius r. Well, here's what we are going to do here. We can find this by saying we are going to rotate the system x of t equals r cosine t, y of t is equal to r sine t, with t being in the interval from 0 up to pi. Right, so think about what that is. That's going to give me the upper half circle, and I take that upper half circle and I rotate it. That gives me my sphere. So now what we can do is we can say, okay, the radius here in this case is going to just be y of t, like the radius in my formula for the surface area. So what we're going to do is we're going to do the integral from 0 up to pi of 2 pi times y of t ds. Well, in this case, x prime is equal to negative r sine t, and y prime is equal to r cosine t. So what is x prime squared plus y prime squared? Well, this, and I'm going to give you a minute, try to work this out yourselves. It turns out that this just comes out to be the radius squared. So what does this come out to be? Well, this is going to be the integral 2 pi times, why am I getting lost here with this thing? We're going to have y of t here, which is going to be r sine t. There we go. I have found where I'm at. And then we're going to have the square root of r squared dt. But this is actually, I've lost my 0 to 2 pi. There we go. Finally, I've found all the pieces that I actually need. Well, this is just going to become the integral from 0, why is that a 2 pi? That should be a pi. 0 up to pi of 2 pi r squared sine t dt. Now, you might think, oh, well, this r squared is really going to mess with stuff. It's not, because r isn't a variable. R is a constant. So all I have to do is find the antiderivative here. So this is actually going to be 2 pi r squared times negative cosine t evaluated from 0 up to pi. And when I evaluate this from 0 up to pi, I pick up another factor of 2. So this comes out to be 4 pi r squared. So the total surface area of a sphere of radius r is 4 pi r squared. You may have seen this formula before, but not really known where it came from. This is where it comes from, and it's relatively straightforward to see it if you use these formulas. Now, if I wrote this in terms of if I wrote y as a function of x, if I wrote like y is equal to the square root of 1 minus x squared, or r squared minus r squared x squared, that would work, and we could do it, and it wouldn't be too bad, but it would be a lot messier than working it out this way using parametric equations. So I would invite you to try to do this by using our old methods, where we would find this by writing y as a function of x. So write out y equals square root of r squared minus r squared x squared, or r squared minus x squared. Why am I suddenly confused by this? Yeah, r squared minus x squared, and then from x equals minus r to r, write out what this comes out to be when you calculate the surface area when you rotate this thing. It's not awful, but it's a lot harder. So it's still a good experiment to make. And it kind of shows you how working with parametric equations can be really, really nice here. By the way, as a bit of an aside, this leads to what are the idea of how do you measure sort of double angles? So how do you measure a two-dimensional angle, if you will, or an angle in 3 dimensions? So for radians, right, for a radian, if I have a circle of length r, or a circle of radius r, then this angle theta is given by, we look at this distance here, and we define theta. If this is my distance along the edge, s, then theta is the arc length along the edge divided by the radius in radians. Well, there is a similar way to measure angles that are sort of double angles. So what I mean by this is if we want to measure in 3 dimensions what happens if you have a sphere, and what if you have like some, we put like a cone in here that cuts out some region on the surface of the sphere. How do you measure how big that cone is? Well, the answer is you use something called stradians, and I don't know if I'm quite spelling this correctly, but 4 pi stradians is 1 full circle. And the reason for that is because the total surface area is 4 pi r squared. Well, how do you measure the amount of the circle you've cut out? You take the surface area A of this little region over the total surface area. And so you measure this in these stradians, so that actually what you want to say is that the area of this region should be equal to this stradians angle times 4 pi times, or not times 4 pi, just times the square of the radius. So, sorry, I'm losing factors of 4 pi as I describe this. But the point is, it allows you to make these kinds of measurements. And this can be an important thing in certain engineering problems or in physics, where maybe we have some sort of a event happening in the center of some space. And the question is, how much can we see of that thing? Like, let's suppose that I have some kind of nuclear interaction and then particles are going to go flying off in all directions. Well, the number of the particles that I'm going to be able to detect depends upon what angle I can look at from. In other words, how many stradians I can cover with my detectors. A full 4 pi detector is literally a complete sphere that detects everything coming out of the center. And so if you can't cover the whole sphere, then you can still answer, well, how many stradians do we actually cover here? For some reason now I'm worried that it's not stradian. It might be stradian. But anyway, you look this up, and it stands for the surface area, surface radians or something like that. So it may not have a T. Maybe it's just stradians. Anyway, that's where that comes from. So what we've done today is we've looked at how we can use calculus with parametric equations, and this calculus stuff with parametric equations. As you can see, it's not really a whole lot of new stuff. In a lot of ways, it's just a revamping of stuff we've done before. And for that reason, I hope that you will find it, something that if you find something confusing, you can kind of think back to, what did I do before in order to make this work? And you'll sort of see what's going on there. If you get a good sense of how to work with parametric equations, the calculus part is usually relatively straightforward. So what we're going to be working on next, and I think we'll probably start in on this next week. I think you've got enough to deal with this week as it is, but we're going to work on another type of coordinate system. Usually we work with Cartesian coordinates. Next time we're going to introduce the idea of polar coordinates, which is a slightly different way of describing the points in the plane. And, well, we'll talk about the advantages and disadvantages to this new system when we get to it next week. So for now, I will stop here. Let me know if you have any questions about these lectures or the homeworks and anything, and I will see you later.